Okay, hello everyone. Welcome to the topology seminar. Today, Kursat Sozer from McMaster University is going to tell us about survey of three-dimensional TQFTs and quantum invariance of three manifolds. So Kursat, please take it away.
First of all, I would like to thank you for the invitation. It's a great pleasure to talk about this survey work, which is joint work with Alexis Viro. We did last year to just write about what is known on three-dimensional three-dimensional quantum invariance. Of course, not possible to cover everything, but like general scheme of things. So I'm gonna talk about what is the big picture of the talk. Is we will focus on, first of all, three-dimensional topology, in particular closed-oriented three manifolds. And the goal of the talk and in general is to like distinguishing different manifolds and how we do distinguish three manifolds, but not finding just homomorphism between equivalent ones, in general producing invariants and checking whether they are strong or not. And then one of the way to introduce these invariants is using quantum topology, ideas coming from physics. And there is a kind of a time scale that I try to draw. Well, maybe before that, I can talk about why three-dimensional topology is like three is in between 2 and 4, and in 2 we know all of the closed-oriented manifolds. They're all classified. There's extensive knowledge of topological knowledge of them. We know all of them by Euler Cartes again, which is. And four-dimensional manifolds, they're not kind of classifiable. There are theorems on that in terms of pi1. They're super general. But three-dimensional topology, there's a rich enough to have rich enough different manifolds, different structures, different geometries, and at the same time computable and kind of classifiable objects. And there's a very strong relationship with physics, even though I don't know almost anything about the physics part of it. All of the things that I'm going to talk about it have quite an interesting physical motivations, mostly from quantum field theory and also from statistical mechanics, quantum gravity, and from conformal field theory. They all have connections to what I'm going to say today from both algebraic and topological point of view, but I don't know details about these connections much, so I will only talk about math side of it. So in this time scale, what happened like before 1984 in Jones introduced like Jones polynomial of nuts. What is known as the Alexander polynomial, which is introduced kind of homological study of the knot complement, and then torsion of manifolds. They were quite studied and helped understanding. Again, when Jones introduced this very interesting polynomial, and then showed that this is different from what is known Alexander polynomial, and from, in fact, very different object, analytical, like von Neumann algebras. And this make a big thing, big impact on the field. People start studying, and then afterwards, Siegel studied and formalized conformal field theory from physics point of view. He formalized mathematically what is a conformal field theory. He puts the axioms, set it up the axioms of a conformal field theory for kind of mathematicians, and in the same lines, Atiyah introduced mathematical axioms for what is a topological quantum field theory. And the quantum field theory is a huge subject, and topological quantum field theories are they're kind of a baby cases. They're the most simplest one, like the all space-time, whatever. It just depends on the topology. There is no metric underlying. So it's kind of a simplified version of QFTs. And in the same year, Witten has this groundbreaking, really good insight on a paper explaining Chern-Simons theory and the Jones polynomial at the same time, from the very physical and at the same time mathematical view of these invariants, and then making connection with a lot of physics. He make this quite a connection, and afterwards Reshetikhin and Turaev like make this Witten's paper and these invariants, computed invariants, more mathematical and explain more mathematical and more rigorous way. They introduce their manifold. They introduce a Reshetikhin Turaev invariants using surgery approach. And afterwards, Turaev Viro, they studied triangulations of manifolds and statistical models coming from physics. Like people worked on this statistical models and states and physics. They used state sum to introduce another TQFT. Later, this TQFT introduced by Turaev Viro using certain categories like UQSL2 that I will talk about later. They're generalized to more general spherical categories by Barrett and Westbury. And afterwards, Migo introduced in early 2000s, what is a center of a fusion category, and then its properties. And later in two different works, Balsam Krylov and Turaev, they make a connection between these two approaches using the center. So the upshot, maybe just what is the big picture. I said a lot of things very fast at the moment. I don't assume people know it. Like this is just a big picture. There are two main constructions of three-dimensional quantum invariants, and one of them uses surgery representations of three manifolds. Like we have if you consider this like S3 in the picture, we have a frame manifold, frame link. And by Mikorish-Wallace, we know that all closed-oriented three manifolds can be obtained by surgery on a frame link. And from this frame link representation, Turaev and Witten, Reshetikhin Turaev invariants produce some quantum invariant of this three manifold. And another approach is triangulating the three-dimensional sphere by three-dimensional closed manifold by tetrahedras and associating some algebraic data to each tetrahedra, and then taking sum of all these possible algebraic data, we get a state sum construction. I will make all of these more clear, hopefully, afterwards. And the key message is there are these two constructions of quantum invariants in three dimensions, and the center construction, algebraic, which is algebraic construction, which builds the relationship between these two, and it says they're in fact under this construction they're kind of yield the equivalent invariants. Okay, they measure kind of the same thing. They're two very different approaches, but the invariants that we get, well, in Witten, Reshetikhin, Turaev, it's kind of more general, but under this equivalence, they're kind of the same. So before moving to the next page, before moving to the next slide, just to recap again, I'm going to talk about two approaches and then the connection between them. Now let's focus on what are the algebraic ingredients behind these two constructions. And we will the algebraic ingredients uses monoidal and certain monoidal or tensor categories, which I will describe now. And there are also this whole object that I'm going to talk about itself is a kind of a new subject, new area like called quantum algebra. People study, they're really quite important questions, and at the same time a lot of progress recently. So let's recall what is a monoidal category. A monoidal category is a category which has objects and morphism as usual. And additionally, we have a tensor product, which is a bifunctor from category C, C to C, and a unit object such that this product operation is not quite associated, but there's an associator, which doesn't have to be, which is, I assume, as an isomorphism for any triple of objects A, B, C in the category. We have this associator, and whenever we take four elements A, B, C, D, there are 5 ways to put a parenthesis among them. And when we put these associators relating each of the parenthesizing way, this diagram commutes. This is the condition that associators need to satisfy. And again, this tensor product is not quite under this unit object, is not quite, doesn't have to be, it can be, but doesn't have to be strictly a unit, left and right unit, unital, but it needs to satisfy up to isomorphism. This is the unit isomorphism, saying that whenever we have like a tensor 1b, we have a tensor, we use here associator alpha, and then here we use right, this is a tensor b, here we use right a, here we use left b, and this diagram is expected to be commuted. So it's like a categorification of a kind of a ring. We have categorification of a like some, in fact, not quite ring, but a monoid operation. So what are examples? There are quite many examples. The main examples: category of vector spaces under tensor product, and category of cobordisms and dimensional cobordisms, where the operation is taking disjoint union, and empty manifold is the unit object. And we have top using Cartesian product and singleton, choosing singleton. And we have set with Cartesian product, or any category with co-product, or any category with products yield a modular category. Well, for each of them that I'm going to talk about, there's a corresponding very useful way of putting a visual understanding of these things, and they are called the Penrose graphical calculus. So what do I mean? Like the way that this all data can be encoded whenever we have a homomorphism in the category, we can represent them by certain graphical diagrams. So when we have identity of an object, we denote by just single strand. And when we have a morphism f from x to y, an object x to y, we denote it by f y. I'm reading from bottom to top, morphisms. And okay, what is what is the tensor product of two morphisms? It's like stacking nearby. Maybe f is x to y, u to v. It's denoted by this is. So how do we denote the unit object? Well, for a unit object, we don't have anything in fact. Like if k is, let's say, a morphism from unit object to x, the symbol for k is going to be like this. Or if L or P is a morphism from element y to unit object, it's going to look like y. So unit object is kind of omitted, and tensor product or the modular product is stacking objects. And the composition is, of course, whenever we have fx to y and let's say m y to z, we have this decomposition. So rigid modular categories or rigid tensor categories are those with the every object comes equipped with a dual object. And so what is a dual object? This is a triple data, duality data is like x star evaluation of x and co-evaluation of x. So evaluation is a morphism from x tensor x dual to unit object, and co-evaluation is a morphism from unit object to x dual to x. So what are examples of these things? Oops. An example is again maybe category vector spaces where the dual is linear dual. We take vector space V, let's say finite dimensional. We need to have finite dimensional, of course. In this case, category finite dimensional vector spaces. It goes to linear dual, and these are the usual evaluations and co-evaluations. Well, another category that we can consider is representations of a finite dimensional representations of a finite group or compact group. And in this case, it's a dual representation. And in this case, our diagram, we have the special objects. Like in this case, it's like evaluation is going to be x star to 1, which we don't put anything. This is evaluation x. And I need to x star, this is to 1, this is evaluation x. And x star x, this is from co-evaluation of x. It's a morphism from unit object to x tensor x star. Okay. And these to be a dual, things, they're not only morphism, but they need to satisfy a condition. And this condition is the usual non-degeneracy of a bilinear product. If you consider this evaluation as, at least in this case, a bilinear pairing, then non-degeneracy of this bilinear pairing in the graphical calculus is precisely this morphism, S diagrams. If we have x, identity of x equals x, and we have evaluation of x in this part, and then we have co-evaluation of x. Here I have x star, x, and x. Well, in fact, what I put under the rug is here, there's a notion of left dual and the right dual. And there's going to correspond to one of them, there's going to correspond to another one. So an object may have left and right dual, and they don't have to be coincide. But in general, the standard examples we have, they coincide, and in a symmetric modular category, they always coincide. And the pivotal category is the tensor category where we can do this by a unique way of finding a unique dual. So this is given by, for every object we have an isomorphism. This is in fact the natural transformation from identity of a category to double dual. And in this case, again, we have a similar examples. As in this case, our diagrams become oriented. Instead of x dual, I'm going to just write x again. Okay. This is again like this one, and this diagram is going to become like oriented. Because we choose like whenever we have a pivotal, we have a kind of we have a canonical choice for of the dual. And in this case, when we look at the closed loops, like for example this one, x dual, okay, sorry, we have x, we have here x dual, we have, when we use right duality again, we have x double dual, and then we have x double dual, its duality is again going to be x. So this is the same as, this is invariant under the transformation. So this is equal to doing x its dual. Like evaluation, co-evaluation followed by. So this is kind of isotopy invariance of closed loops. This equivalence gives an isotopy. Whenever we have a pivotal category, and whenever we have a diagram, we get an isotopy. The moves are independent from the isotopy of the graph. And spherical ones, spherical categories are those pivotal categories plus left trace and right trace of every endomorphism is the same. So, and the examples are kind of similar, I can think of. And so what do I mean by left trace of a morphism? F is a morphism from X to X. So we can take its co-evaluation and then evaluation. So we get this morphism. This is a left trace of F. In a similar manner, we can do this. Left trace of it. So this is a morphism from, these are endomorphisms of K. And we claim they coincide. And this is for every F, for every endomorphism of an object. In this case, we call the category, if this is the case, we call the category spherical. And why, you may ask why, where does it come from spherical? Because under this condition, whenever we have kind of closed loops on sphere, like we have, by doing this, like you can think of this, the relation, the equivalence between this, taking this around the sphere to come it back. It's like, this is now, in this case, now the isotopy invariance of loops on a sphere. Then we put loops on a sphere, that's why it's called sphere. And in this case, when we have spherical category, dimension of an object, like when we have an object X, its dimension is just evaluation followed by, when we have an object X, its evaluation is just evaluation, co-evaluation. This is maybe dimension of left. Using left dualities, left dual data, we get a left dimension, but spherical, this is the same as the right dimension, then we are able to define dimension of an object. When we have a category with duals, we can define, if it is spherical, we can define, when we have a pivotal category, we can define left and right dimensions. If the category is spherical, we say that these two dimensions of an object must coincide, and then which we call dimension of an object. Now, is there any questions at this point? Am I going a bit fast? Now, at the moment, we start from this, most general model categories, and then we end up with spherical categories, where what do we have? We have a dual, like we have a tensor category for which every object has a dual, and then we can do this coherently by pivotal structure. And then spherical means left and right duals are the same, traces all coincide. Oh, sorry, left and right traces are always. So for more examples that maybe I forgot to mention, representations, cobordism categories, topological category of spaces and morphisms, or we can consider more as a rigid or pivotal categories, twisted categories, representations of quantum groups, and more. And next, from spherical to fusion. So fusion is a little bit more. A fusion category is the one where all morphism spaces are K-linear. They are vector spaces over fixed, let's say fixed field K, and they're rigid, but it's rigid. And in this case, also composition and tensor product are bilinear. And semisimple category is the one where every object can be written as direct sum of I don't know, n of xn of other objects. Every object has a decomposition in terms of other objects, and one can make sense of these in a category using inclusions and projections as the usual way. Yeah, I will not do that. And the most crucial property of condition on fusion category is the fact that there are only finitely many simple objects. Well, not only finitely many, but This is up to isomorphism. Isomorphism class of simple objects are finite. So what is a simple object? An object, simple object, I in a category, semi-simple category C is the one whose endomorphism is just isomorphic to K. And that another condition is that unit object, unit of the category, this tensor category, is simple as well. Unit is simple. Here again, category examples, kind of vector spaces, finite dimensional vector spaces, or they're twisted by third cohomology element, where H3, oh, sorry, sorry, category vector spaces or category of G-graded vector spaces. And here, their twisted version is like H3G K star. And more examples are representations of finite group or compact group, or representations of finite groups, or representations of finite dimensional Hopf algebra. And there are more examples as well. So in this case, what do we know? What do we know about Penrose's graphical calculus is the following. Whenever we have some closed diagram, like we have some maps, GH, this is an element of endomorphism of one, which is K. So for any closed loop in a category, we can assign a number, because a unit object is simple, and we denote the collection of these representations of finite many simples as I. Elements are like I1, In. These are representative of simple objects. And the ribbon category is a fusion category with a braiding. Well, it's a braided monoid category, where we denote CXY as braiding notation is like this. And it needs to satisfy a hexagon condition that I'm not going to write, and a twist isomorphism for each object. We have twist isomorphism, and it's graphically it's defined like so. We have here a braiding and a cup for X, like co-evaluation for X and an evaluation of X. This is an element of endomorphism of X, this category. So if X is simple object, so it is some, if X is a simple object, then it's going to be some element of the underlying field. And the modular category, the most important one, is a ribbon tensor category, such that it's non-degenerate. It has non-degenerate S matrix. So what is S matrix in this case? When we have I is a set of simple representative also finite many simples, because ribbon is a fusion, and fusion has finite many simple objects. And then what is this S matrix? S matrix has, let's say, Aij, where I and J is an element of this representative simple objects. We form a Hopf link where this is I, this is J. So what we do, we have co-evaluation of I and co-evaluation of J, and we braid them, and we use the inverse of the braiding, and then we again apply evaluation of I and evaluation of J. So this is overall is an element of unit object which we know is a simple, so it's an element of underlying field. So this is kind of some number. And S matrix is the n by n matrix, assuming there are n many symbols. And it is given by Hofling representations of the graphical calculus of the simple objects. So it is n by n, like underlying n by n matrix consists of underlying fifth elements. And the fact that it's non-degenerate, it's about this matrix is invertible. Or another way of equivalent to saying this, equivalent way of saying this, trivial Muegge center. Which says that there are those objects in the category which commute with everything under braiding, well, which have trivial braiding with everything is a trivial category. There is no object in this ribbon category which commutes precisely with everything else. So that it has a trivial Muegge center. So, and as an example, representations of quantum groups at roots of unity. These are examples of ribbon and modular categories, or as I said, G-graded vector spaces, or representations of finite groups. And the point is here, we need to choose roots of unity, because if you don't choose a root of unity, if you take a compact Lie group or its Lie algebra, its representations are given by weights, and the weights are infinite. So simple objects are going to be infinitely many. That's why it doesn't work. Like simple representations are going to be given corresponds with like weights, simple weights, and then they're going to be infinite. But if you take a deformation of them and evaluate at the roots of unity, there's a bit involved process of modular negligible ones, and then showing semi-simple quotient, taking semi-simple quotient. We have only finitely many simple objects, and at the same time, all these constructions preserve semi-simplicity of the category. So these are kind of the main examples that produce quantum invariance, algebraic things. So this was kind of all so far, all of the things with like algebraic parts. So what is a three-dimensional TQFT? It's a functor from three-dimensional cobordism category to category of vector spaces. So what are objects in here? Objects are closed-oriented manifolds. Anamorphisms is precisely cobordisms that bounding is closed oriented surfaces. And when we apply Z, what do we get? We have sigma prime. Under Z, it's going to be some vector space. It's another vector space. And Z is going to associate it to it a linear map. And the monoidality says the monoidal operation here is disjoint union, here tensor product. Whenever we have the sigma, we're going to have Riemann tensor Z sigma prime, or as a cobordism, whenever we have, sorry, the union of two cobordisms, their product is going to be and a duality is when we reverse the orientation, it's going to be dual of the corresponding linear vector space. And the gluing is what is the composition in this category? In this category, composition is gluing manifolds along the same common boundary. Say we have sigma, here we have sigma prime, and we have, let's say, torus in here, it's boundary, sigma double prime, and then when we apply Z to omega, let's say W prime, W compose W prime is going to be this is nothing to do with monoidality, but just being just a functor. So what does it say? Like these invariants, whatever these things, if we call these linear maps as invariants, they're going to be behaving well under cutting and pasting, because if you have this whole manifold, if you cut along this, it's going to distribute over this composition. It's going. And the most important thing is maybe the fact that monoidality, it implies here the unit object is empty manifold. Here, the unit object is just, say, complex vector spaces, so complex numbers. It says image of unit object is going to be C. So whenever we have some three manifolds, which doesn't have any boundary, closed oriented three manifold, M, then this is a morphism from empty manifold to empty manifold, and under Z, this empty manifold is mapped to C. This one maps to C, and this linear map between two one-dimensional complex vector spaces or any vector space is determined by the image of one. So this data is precisely a number, and that number is the invariant of this three manifold. This is the quantum invariant of this three manifold. And this composition, why it's important, because it says a priori this number can be computed by cutting into codimension one manifolds and gluing back them in cutting along codimension one manifolds and understanding these pieces and then gluing back them. So it's kind of a theoretically there, it's computable. It has a computable nature. So I'll start giving this recipe for the surgery case. Okay, the first one. So we know what is an underlying algebraic tools, and we now we know what is a TQFT is a monoidal functor, and this approach is Atiyah's. This is Atiyah's formulation, inspired from Siegel's formulation of conformal field theory. So what we do, we present the given closed tree manifold by a dense surgery on a framed link. So we have a link, like we encode the framing, like a blackboard framing. We put these twists to encode the framing, and then we say M is obtained from surgery on this link. So we pick a modular tensor category, which is rigid, fusion, and S matrix is invertible. And what we do, we color each component of this link by the Kirby element. And the Kirby element is, remember, this is a collection of simple objects. This is the representation set of simple objects. Over all simple objects, we have a dimension for each object. And we take sum of, you can think of this direct sum. This is a Kirby element, direct sum of dimension of this object with itself, and then we color each component with this object. And next, use the R matrix. R matrix is going to give the braiding. Okay. Since we have only simple objects, we need to understand braidings on the just simple objects. And then this, between two different objects, the R matrix is precisely the braiding data. Then we evaluate this, as remember, this is in the categories T, this is like endomorphism of the simple object. So we are going to do this evaluation. And this is just linear combination, so everything is linear, these are linear categories. So this makes sense. This is just an endomorphism of K, and this is a simple object, this is fusion, so it's K, so we know this. But of course, this computation is not easy because the R matrices are kind of complicated and not easy. Using twist, we import this information. Like here we have co-evaluation for every object in here, and then we twist, we put R matrix in here, we put twist in here, and then co-evaluation, we compute, so we get something. That's a kind of computable process. And then in this case, we do normalize to make sure that this invariant is invariant under different representations. We know two different representations of three manifold under a frame link is related by Kirby moves. And to show that they are in this invariant, this number is invariant under this thing, that computation that we do is invariant under Kirby moves, one needs to do normalizations, and normalizations are given by this. And theta I is precisely the number, since we are simple object, this is an endomorphism of I, which is K. These are precisely the number that corresponds to this test. And the next state sum, how do we compute the state sum? In this case, we pick an oriented triangulation of the closed three manifold. And before we chose, in the surgery case, we chose modular tensor category. In this case, we choose a spherical fusion category. And what we do in every edge, we assign, like, let's take this tetrahedra. In every edge, we assign a state. A state is a simple object. Okay, there are only finitely many simple objects apply isomorphism. We assign one state is like consisting of assigning edges, simple objects, and then we assign data for each state. We assign a number to each edge, which is just dimension of this object. You know what is the dimension in the tensor category of an object. And for each tetrahedra, we assign a 6J symbol, which can be computed again by diagram calculus. It's another number. In this case, the partition function, or the Turaev invariant, is dimension of the category, which is, I did not define, but dimension of a category is simple objects, dimension I square. For any simple, there are finitely many simple objects, and if we take sum of, we square, there is a sum, and then we get this, and the minus the number of vertices, and over all states, we take products of these dimensions of the edges for every edges, and we multiply with the 6J symbols at each tetrahedra. And the fact that sums are finite because there are only finitely many simple objects and there are only finitely many edges. And this sum is finite. So this is in fact invariant under different triangulations using Page's modes. So kind of the recipe is like using again certain graphical calculus very wisely and making sure these are invariant under the topological relationship between these two, surgery and triangulation constructions. So the upshot is these two are related. So Dirichlet center of a category consists of object in the category plus a half braiding. And half braiding is a kind of natural transformation from other objects to itself. So this should think of as the center of a tensor category that collects all objects that commute up the covariant half braiding. Like it consists of objects and plus the data of one half braiding with all other objects. And Müger proved that if C is spherical fusion, then its center is modular. And in fact, the dimension of the center is the square of the dimension. And the equivalence, the main theorem, is proven by independently Balsam Kirillov and Turaev is that state sum invariant on this spherical fusion category is the same as Witten, Reshetikhin, Turaev surgery invariant of its center. Like in the case of G-graded vector spaces, its center is representations of its quantum double of the group. And then it can be computed. In this case, it's going to give the correspondence and this Witten case. And the philosophy here is like taking center of a fusion category is like taking square, which makes a topological locality because we have a triangulation which captures more local data, which turns into this local local data into algebraic non-degenerates, like algebraic non-degenerates, like S matrix invertible. And why this is topological locality? Because when we have tetrahedra, things are more local. And lastly, just some generalizations of these works and then different perspectives. I will there are various different ones, but maybe most studied ones are what the followings and different directions. One is extended TQFTs. Like instead of two-dimensional case, not three dimensions. Not easy to draw in three-dimension, but two-dimensional cases like extended can be think of as like manifold with corners. Instead, before we were cutting manifolds along codimension one-flat manifolds, and they were behaving very well under these operations. In this case, one can cut more dimension manifolds and then get invariants. And in this case, there are really many works on this area. And homotopy QFTs, instead of cobordisms and morphism between them, we fix some topological space. One considers maps to those invariants and then finds invariants of these maps. And in a non-semi-simple case, one considers more general categories. Like one removes the semi-simplicity condition, and which gives a stronger quantum invariance. And in defects and domains, one has again a maybe three-dimensional TQFT, but in this case there is maybe some strata. And in this data, in this case, one associates different algebraic structure to each and computes more physical things. And lastly, I can say a recent work on mine with Alexis Viro, we generalized this homotopy QFTs from one types to two types. So whenever we are given a topological, whenever we are given topological space, we have pi1, pi2, pi3, pi4, and this kind of captures all of the algebraic data. And in the level one, if everything else all vanish, they're zero. If pi1 is non-zero, this is called one type. If pi1 and pi2 are non-trivial, this is called a two type. And in the case of one types are in bijection with discrete groups, and two types are in bijection with cross modules. This definition is written here. And what we did with Alexis Viro is to generalize the work in one type case, like BG case, to two type case. And we generalized so far we introduced corresponding algebraic categories, cross-modular graded categories, and we studied certain Hopf-graded algebras whose presentation yields such categories. And also we construct 3D state sum case, state sum HQFT with two type targets, and we generalize the TQFT case. TQFT case is just a special case in this case, and we make this generalization, and currently we are working on generalizing Cooper-Brigg invariant. And hopefully afterwards, we plan to work on surgery TQFT, and hopefully our major goal is to find this correspondence under center construction in this setting. And that's all I want to say. Thank you for your attention.
Okay, perfect. Thank you, Kursat. So let's see. Any questions for Kursat?
Thank you.
Okay, I guess I have one question. So is this state sum, is it something that's used by physicists? Is that a construction like what does this
Yes.
mean there?
Yes, the state sum. Yes, the state sum is it has origins from statistical mechanics. They study states on different things, and then it has also connection with quantum gravity, but I don't know the details. Yes, they're coming from physics.
But the things that you associate with simplicial complexes is just numbers, right? So you said this edge is the dimension of some.
Like it for each edge we assign a simple object. A state means for each edge we assign a just a simple object, and this object has a dimension. When we compute, we take product of these dimensions over all edges.
Why? Okay, then I misunderstood. So what do you assign to a triangle?
We assign the triangle is another number, which is a 6J symbol. Because again,
Oh, okay. It's not a it's just a number, not a simple object or anything like that.
Yeah, for triangle we have again for each tetrahedron. For tetrahedron we don't assign anything. For a triangle we don't assign.
Oh, okay.
For a tetrahedron we have a 6J symbol, which is a number. And this maybe the idea that the physics that I know is like whenever things come from physics, there's this partition function and summing over all things. Like this is the idea. Like one defines the states and consider one should consider all possible ways of doing the states, allowed states, and in real life this is not finite, and this is about like well-definedness of measures on the space of states and whatever. But in this case, in this Turaev and Viro takes physicist works and then make it finite case, and in finite case we can take sum and I show that this is invariant under the moves. In the same way, in the Witten Reshetikhin Turaev, this corresponds to the Chern-Simons theory. So this is kind of some like I don't know, some flat connection taking integral over all. This is a flat connection, and then I forget, right, some functional here and taking integral of this functional over all spaces, and it gives a name. Like this is what I want to write. This should be Feynman integral. Well, I'm sure he's gone now, but Ilker could explain this much better. But this is like whenever things come from physics, there is kind of assigning a state and considering all possible states and summing all over possible ways of doing things is invariant how one construct the thing itself. So I don't know. This is the knowledge of physics that I know.
Okay, so in the main, I think you call the bridge between the two constructions. Can you go back?
Yes. Yes.
Yeah, I just want to see. Okay, maybe I can get a bit more intuition by looking at the example. So can I take G to be a finite group there? Then is the Grimfeld, is it the double? Is
Yes.
it quantum double or something?
If you take yes, exactly. If you take a G-graded vector spaces, then as a spherical fusion category, then its center is the representation category of quantum double of the G.
But so this DG is supposed to be a Hopf algebra, right? Is that true, or is it?
So
Is
yeah,
Hopf?
Yes. Here one can consider G as KG.
Oh,
Like
okay.
group ring.
Nice.
We like we consider this as modules over KG, or represent by representation means I mean modules over Hopf algebra. Like or finite dimensional Hopf algebra, it gives a fusion category. It's this works as you said. Yeah, this works in the finite dimensional Hopf algebra, and it's the quantum doubles.
The center construct on the left is the center of the category, right? So the center.
Yes.
So the center of a category. How should I think of this? Because starting from C, so these are G-graded vector spaces. And the center.
There are.
Okay, maybe I should ask it this way. I mean, is it possible to see this state sum versus this more categorical this how should I call it this link construct or surgery construction in this example immediately, or is it not very clear on this picture? Because I mean, I guess you assign these invariants in the theorem, right? And they turn out to be equal. So could you tell what these numbers correspond?
In this case, in both cases, what should correspond is 1 over G, like
Okay.
of
The size of the group, basically.
pi 1 ups home pi 1 ups G to pi 1 of M. Like this graph Witten invariants.
Oh, okay.
Accounting, I would yeah, it should, yes.
Okay, let's see. Pi 1 of n.
Counting kind of homomorphisms of
Okay, so could it be from, okay, I mean, I don't know this stuff, but I felt like it could be from pi 1 of m to g, but probably not, right? This is,
yes.
yeah, okay.
You're
Because,
right.
because,
You're right. You're
the
right.
reason, if you take,
Yes.
so there's these, the reason I thought it would be because, people are interested in like commuting elements in Lie groups. And I think these are maybe initiated from these homomorphism spaces that come from here. I think there's a connection. But anyways, okay. Okay, I think that makes more sense, at least to me. Okay, well, I mean,
Yes.
I guess that's all my question. Well, thank you very
Yes,
much.
but maybe one point I can make it, like in this construction, yeah, we say kind of they're kind of measuring the same thing, but this equality kind of shows that this Witten Reshetikhin triangle is kind of stronger, in the sense that every triangulation invariant or say some invariant can already compute from this way, but there may be some modular tensor categories which are not center of something. So they may have more invariance in a sense. From this perspective, one can say state sum invariant is kind of can be always derived from Witten Reshetikhin, but if the modular tensor category is not centered, then maybe Witten Reshetikhin tribe invariants are kind of strong in some sense. Yeah.
Okay.
But at the same time, they are maybe harder to compute or
I see. But so, okay, so maybe can I ask also the topological locality? I guess you gave some intuition for that, but algebraic non-degeneracy, you said S invertible. Is that what did that mean?
so maybe this is very this sentence is like when we have triangulations and when we have triangulations, one can already think of like we already cut the manifold into lower simplices in a coherent way. Like we have one simplicity, zero simplicity, and one. So things are kind of more local. If one establishes how to put, well, in fact, there are works on this, how to put some algebraic data on the vertices, and from this recover algebraic data on the edges, and then algebraic data on the covers, and then one can maybe. This is more open to assigning local data and recovering whole TQFT or whole manifold invariant from this data from as data assigned to points or zero simplices or just edges. So this is kind of maybe key point of state sum. It's more easy to make extended TQFTs or more understandable to extend TQFTs in the setting. And on the other hand, in the case of surgery case, the non-degeneracy is the key point. Non-degeneracy of the S matrix is the key point. And then, so this center construction takes one to another. That's like, it takes this topological locality on this crucial property of the state sum to non-degeneracy of the modular tensor category or Witten Reshetikhin tribe. It does not say more on this. What does this like? Kind of philosophical, but I don't know. It makes a connection between these two things, and the crucial properties of these two things is one of them is like more local in the sense that we have triangles, and triangles have faces, which like there's already candidate to assign this extended data maybe. And the other thing is the crucial thing is the non-degeneracy of the S matrix.